All right, well, thank you all for coming. It's so great to see you all here. Before I start, I did just want to say that everything I'm talking about today is in collaboration with and developed under the incredible mentorship of Adam Marcus. All right, so the title of my talk, as well as the title of my dissertation, is Hermitian, Non-Hermitian, and Multivariate Finite Free Probability. So finite free probability is a fairly new field, but it does have a lot of connections to many longstanding fields of interest, including random matrix theory, free probability, classical probability, polynomial convolutions, and applications to physics and computer science. I'm going to touch on all of these connections sporadically throughout my talk. All right, so first I'm going to start with a review, mainly of linear algebra, but from a perspective that might help motivate and contextualize finite free probability. So what is finite free probability? So finite free probability studies sums and products of unitarily invariant random matrices. So to parse this a little bit, the word finite is there because the random matrices we're going to be studying are finite dimensional square matrices in this case. Lowercase n is going to be that dimension. Free has a meaning from free probability, but when you can extend this concept to the finite dimensions, and it's essentially generalized to mean unitarily invariant. So finite free is kind of like a fancy way of saying finite dimensional unitarily invariant random matrices. We're not just going to be studying individual matrices here. We're going to be interested in sums and products of these random matrices. And when we do that, we start to uncover algebraic structure like central limit theorems and Brownian motions that's very similar to classical probability, which is why the word probability is there. That's also, that type of analogous structure is also why the word probability shows up in free probability as well. So we're studying matrices. So what is a matrix? Just some review. A matrix represents a linear transformation with respect to some chosen orthonormal basis. So here I have some linear transformations, so categorized where Hermitian transformations are just like scaling your underlying space. Unitary transformations just rotate your underlying space. And then non-Hermitian transformations both scale and rotate. So really the name just means all possible transformations, but we specify because Hermitian ones are so commonly studied. But to represent these linear transformations as a matrix, you need to also choose some underlying basis. So in this first example here, I choose the basis R1, R2 perpendicular to your screen, and then I can represent this linear transformation with the matrix A. But if I have the same linear transformation, as you see here, and I choose a different underlying orthonormal basis, like U1, U2, then I can represent this linear transformation with the matrix B. So we say that A and B are unitarily similar matrices if they represent the same underlying linear transformation, only with respect to different orthonormal bases. So unitary similarity has a lot of nice properties. One is that it forms an equivalence class. So if A and B are unitarily similar and matrices B and C are unitarily similar, then A and C are unitarily similar. And also, if you have a unitarily similar equivalence class of Hermitian matrices, then one of the matrices in that equivalence class will be a diagonal matrix with real entries on the diagonal. And those real entries are the eigenvalues of any matrix in that unitarily similar equivalence class. So what that means, of course, is that then any of these unitarily similar equivalence classes can be uniquely identified by the collection of eigenvalues of any matrix in that equivalence class. So if you're coming to this talk from a linear algebra background, you might think, oh, well, I know another way to store the information of those eigenvalues. I can store them as the roots of the characteristic polynomial. And what we mean by storing them as the roots of a polynomial means instead of keeping track of what the roots are, what the eigenvalues are, we're keeping track of what the coefficients of that polynomial are. And those coefficients also have another name. They're called elementary symmetric polynomials, and they're functions of those underlying eigenvalues. But if you're coming to this talk from more of a probability background, you could think, oh, well, given that collection of eigenvalues, I can put a uniform distribution over those eigenvalues and uniquely represent it by its moments. And of course, so that's really just knowing those moments is equivalent to knowing the coefficients of the moment generating function. So in this view, you can kind of even think of the characteristic polynomial as the elementary symmetric polynomial generating function. And one nice property is that you can go back and forth between these two ways of thinking using something called Newton's identities, which give you a direct way of going back and forth from the coefficients of the characteristic polynomial to the coefficients of the moment generating function. and you don't actually need to find the roots of that underlying polynomial or the underlying distribution given those moments. You can just go straight from the moments to the elementary symmetric polynomials using Newton's identities. So these are all ways to characterize the unitary invariance of a single matrix. But as I said in the beginning, in finite free probability, we don't just care about individual matrices. We want to study sums and products of these matrices. And even if I know all of the eigenvalues of two Hermitian matrices, that doesn't uniquely determine the eigenvalues of their sum, for example. So here I have 3 examples where I know that the eigenvalues of each of these matrices are 1 and 2. All of these matrices that I'm adding together are Hermitian matrices, and yet the eigenvalues of the sum in the first case are 2 and 4. The eigenvalues of the sum in the second case are 3 and 3. And in the third case, I get this. So just knowing which unitarily similar equivalence class my original matrices started is not enough to know what unitarily similar equivalence class their sum ends up in. So to get over this, what I define, I define a unitarily or a unitarily invariant product and a unitarily invariant product. So the way I do this is that given my matrices A and B, instead of just adding those matrices A and B together, I uniformly at random pick a matrix in the unitarily similar equivalence class containing matrix A. And I also uniformly at random pick a matrix in the unitarily similar equivalence class containing matrix B. And then I add those random matrices together, or I multiply those random matrices together, as I show here. But then what I get out is a random matrix. So that random matrix only depends on the equivalence classes I started with, not on the individual matrices. So it only depends on the eigenvalues of the starting eigenvalues I had. But now I get a random matrix, and the unitarily similar equivalence class that random matrix ends up in, there is a distribution over many possible unitarily similar equivalence classes. This distribution over equivalence classes is equivalent to what more or less equivalent to what people in random matrix theory call the empirical spectral distribution of a matrix. And if you've studied random matrix theory, you know that knowing the empirical spectral distribution of a random matrix is really hard and only really known for very special matrices, and truly almost never known if you're interested in sums and products of random matrices. So this is a really hard problem. So people have tried to make it more tractable. Sorry about the sirens. More tractable, given taking different approaches to make it more tractable. So one approach is to only study this where the matrix dimension goes to infinity, and in this large dimension, this is equivalent to what is called free probability. But in this talk, as I said, we're not just studying free probability, we're studying what we call finite free probability, where we care about the finite dimensional aspect of these matrices. So random matrix theory, the most common way to make this problem more tractable in random matrix theory is to, instead of studying the empirical spectral distribution, you study the expected empirical spectral distribution. So really what the expected empirical spectral distribution does is it takes away the correlations between eigenvalues of this random matrix. And in so doing, you also lose the information about the underlying dimension of your random matrix. So just to give an example, if I have a random matrix A, where its eigenvalues are 1 and 6 with probability 1/2, or its eigenvalues are 2 and 5 with probability 1/2. So this fully describes its empirical spectral distribution, but its expected empirical spectral distribution is a single collection of values, 1, 2, 5, and 6. So you see here that we've lost the underlying dimension information, and we also lost the fact that the 1 came with the 6, it could have come with the 2. We no longer know here. Algebraically, one way to define the expected empirical spectral distribution is to take the moment generating function and take the expectation of that moment generating function. And then, so really I'm taking the expectation of all of the coefficients of that random moment generating function and defining that expected moment generating function to be the moment generating function of my expected empirical spectral distribution. So the moments of this are just the expected moments of the underlying empirical spectral distribution. So that was one approach, which used the moment generating function approach. But another approach that we have is to take the expected elementary symmetric polynomials of this, or the expected characteristic polynomial. So looking at the same example, I have my same matrix with eigenvalues 1 and 6 with probability 1/2 and 2 and 5 with probability 1/2. So I take the characteristic polynomial corresponding to eigenvalues 1 and 6, the characteristic polynomial corresponding to eigenvalues 2 and 5, I take their expectation, I average them together, I get this new polynomial. This new polynomial is still of degree 2. So I still keep the fact that my underlying matrix was a 2 by 2 matrix. So that's a nice change from before. And also, if you look under the hood and see what the roots of this polynomial are, they're like 1.4 and 5.6. They keep some sense of the correlation that's going on in this random matrix. So these seem like nice case, at least in this specific case, nice advantages of the expected characteristic polynomial as opposed to the expected empirical spectral distribution. So now I want to apply this expected characteristic polynomial approach to our original random matrices we cared about, which were the unitarily invariant sum and unitarily invariant product. So here I've written that out, and I define the finite free additive convolution represented by this box plus to be a function on my original matrices that takes the expectation of the characteristic polynomial of the unitarily invariant sum. And I do the same for the, with this box times is the finite free multiplicative convolution, which gives me the expected value of the characteristic polynomial of my unitarily invariant product. As you see, these convolutions aren't functions on the underlying matrices, they're functions on the characteristic polynomials of those two matrices that I'm convolving. And even more amazingly than the fact I can define it that way, is that they actually define polynomial convolutions. So what I mean by that is, given the coefficients of my original two polynomials, a direct function of those coefficients gives me the coefficients of their finite free additive convolution, or in this case, the coefficients of their finite free multiplicative convolution. So I don't need to ever find the roots of these two polynomials. I can just get straight from the coefficients to the coefficients. Also, a nice property here is that instead of taking a unitarily invariant sum, if I take a sum over the equivalence classes over the orthogonal matrices or over sign permutation matrices, I get the exact same convolution for the expected characteristic polynomials. This is interesting because physicists really care about this orthogonal equivalence class, and computer scientists studying random graphs care about this equivalence class over sign permutation matrices. So the study of these two underlying convolutions really is what Hermitian finite free probability is. It's just studying these two convolutions. So let's look at some of the algebraic structure of these convolutions. So with respect to the polynomials being convolved, both of these convolutions are commutative. They're also linear with respect to those polynomials. And I can define what I call a basic polynomial, which is just a polynomial with a single root of multiplicity n, where if I take the finite free additive convolution of two basic polynomials, I get another basic polynomial whose root is just the sum of the roots of my original basic polynomials. And if I take the finite free multiplicative convolution of basic polynomials, I also get another basic polynomial whose root is just the product of the original roots of my basic polynomials. So taking this linear and basic polynomial, these observations about basic polynomials and linearity, I can give you the first theorem of today, which I call basic polynomial decomposition, which basically says if I want to take the finite free additive or multiplicative convolution of two polynomials p and q, I can decompose them into a weighted sum of basic polynomials. This is in no way a unique decomposition. It works for any decomposition that satisfies this equality. And I can then write the finite free additive convolution as another weighted sum of basic polynomials, or the finite free multiplicative convolution as this sum of weighted basic polynomials. And a corollary to this theorem, if I add an extra constraint that the CJs are all positive and sum to 1, and the DKs are all positive and sum to 1, then I can write this in a language that relates to classical probability, where if I give you a classical commuting random variable S, whose moment satisfies some set of constraints such that this expected polynomial I wrote here, where S is this random variable, some random variable with moment satisfying this, and I do the same for T, where T is a random variable satisfying this equality when I take the expectation of this polynomial, then the finite free additive convolution can be written in terms of adding independent classical random variables. So here their convolution is just where I take the sum of S and T, where these are independent commuting random variables from classical probability, and the finite free multiplicative convolution can just be written as this expected polynomial, where here I take the product of these independent commuting random variables from classical probability. So using this connection to classical probability, I can now prove the finite free additive central. Oh, so I should say that this corollary was previously derived by Adam Marcus in 2016, not using basic polynomials, but using directly facts about independent commuting random variables. The basic polynomials let you do a few other extra things with flexibility that I don't think I'll get a chance to talk about today, but it's a slightly different approach. So now I can use that connection to classical probability to prove the finite free additive central limit theorem. So here I have a sequence, a collection of capital N matrices, all of which have some underlying constraints on the first two moments of those matrices. I scale each matrix by 1 over square root of capital N, where that's the number of matrices. This is like you do in any other central limit theorem. You scale by 1 over square root of capital N, and then I take the finite free additive convolution of all capital N of these characteristic polynomials, these scaled characteristic polynomials. And as I take the limit as capital N, the number of matrices goes to infinity, it converges to this polynomial, which I write as an expected polynomial, where this is a random variable here that is distributed according to the Gaussian distribution, which is, of course, the additive central limit theorem of classical probability. So this really has a direct connection between the finite free additive central limit theorem and the additive central limit theorem of classical probability. And actually the proof follows directly from the classical proof of the classical central limit theorem and from the connection to classical probability from the last slide. So as I said in the beginning, finite free probability connects to a lot of related topics, so other fields. So I'm going to just discuss some here with this polynomial. So it connects to polynomial convolutions and study of polynomials. In fact, this expected polynomial has a name. It's called the Hermite polynomial. If you've seen them before, you might have seen it written in terms of differential operators, but this is another way to write it, where S is a Gaussian distributed random variable. It's related to random matrix theory because the expected characteristic polynomial of any Wigner matrix in random matrix theory is a Hermite polynomial. Also, it's related to free probability because if you look at the roots of the Hermite polynomial, of a degree n Hermite polynomial, and you let the degree go to infinity, then the distribution of those roots converges to the semicircle law, which is the additive central limit theorem of free probability. So our finite free additive central limit theorem converges to the free additive central limit theorem, as we might want, and it's related to physics through Gaussian beta ensembles, which relate to quantum energy levels of heavy-tailed atoms with heavy nuclei, and it's where that distribution crystallizes to the roots of the Hermite polynomial as beta goes to infinity. And I say crystallizes because sending beta to infinity is like sending temperature to 0. So they like freeze to those, to the roots of the Hermite polynomial, that distribution. All right, so also now that we have the finite free additive central limit theorem, we can define finite free additive Brownian motion, where I define my Brownian motion polynomial, where my parameter that was sigma squared, I just replace it with a t, where t can be any real value or any value really. And now to perform Brownian motion on a polynomial, I say, give me any polynomial p of x with roots lambda 1 through lambda n. Then if I convolve that with the Brownian motion polynomial with parameter t, they evolve smoothly with respect to t according to some point process. And I can write the differential point process here of how those roots move as I convolve with the finite free additive Brownian motion polynomial. And this might look bizarre, but it actually shows up in the literature. It's Dyson Brownian motion, where once again you send beta to infinity. And this has connections to physics and to random matrix theory, which were observed originally by Dyson. This connection between polynomials and additive and Dyson Brownian motion was also derived by Terry Tao in 2017, where he looked at it as derivatives on polynomials, not from this finite free or random matrix perspective, but this found the same connection between polynomials and Dyson Brownian motion. All right, so that's what I'm going to say about the finite free additive convolution. Now for the finite free multiplicative central limit theorem. Once again, I have a sequence of capital N matrices with some assumptions, but now I scale each matrix not by multiplying it by 1 over square root of n out front, by raising each matrix to the power 1 over square root of n. And then I take the finite free multiplicative convolution and send the number of capital N times and send the number of matrices capital N to infinity. And it converges to this polynomial, which once again I write as an expected polynomial, where this random variable is distributed according to the log normal distribution, which is the multiplicative central limit theorem of classical probability. The hard part in this proof is really computing this scaled polynomial, this exponential, the characteristic polynomial of this exponentially scaled matrix, which we do using some combinatoric identities and leveraging Newton's identities. So let's talk about how this relates to these corresponding fields. So it relates to the study of polynomials in the fact that if sigma squared, our initial assumptions are greater than or equal to 0, all the roots of this polynomial lie on the positive real line. If sigma squared is less than or equal to 0, all the roots lie on the complex unit circle. It relates to free probability because the distribution of the roots for this polynomial, as you send the degree of these polynomials to infinity, converges to Bian's free unitary Brownian motion operator in free probability, as you would hope. Also, a kind of surprising connection is that under a change of variables, this polynomial is equivalent to the partition function of the Curry-Weiss model. And the Curry-Weiss model is just another name for the Ising model on a complete graph. So that's another interesting connection. Just as we did with the additive convolution, we can define now a multiplicative finite free Brownian motion polynomial, and start with any other polynomial p of x, where its roots are e to the I theta 1 to e to the I theta n. I could have written it as lambda 1 to lambda n. It just looks nicer in this form. And then say Brownian motion on these roots is how they evolve as I convolve with this finite free multiplicative Brownian motion operator. And I get the differential point process on these roots. And this, once again, might look a little bizarre, but it shows up in the literature. It's the differential point process of unitary Brownian motion, also discovered by Dyson to have connections to physics and random matrix theory. And this connection between polynomials and unitary Brownian motion was also previously derived by Terry Tao in 2018, also from a perspective of derivatives, differential operators on polynomials, not from this finite free or matrix perspective necessarily. All right, so when I got into studying finite free probability, the studying of these two convolutions, at least when you're interested in eigenvalues, was really where finite free probability stood. And I started to ask the question, well, what if I wanted to use finite free probability to study non-Hermitian matrices that represent non-Hermitian transformations? And I started to see that these convolutions alone weren't quite enough. So I'm going to present and then the new convolutions that come with that. So let's just look at what happens for non-Hermitian matrices. So here I have two matrices, A and B, that are not unitarily similar. This is clear because any unitary transformation on the matrix A will just give me back the all zeros matrix, which is clearly not equal to this matrix B. And yet, even though they're not unitarily similar, they have the same eigenvalues, they have the same characteristic polynomial, therefore, they have all their moments are equal. So our old way of looking at this couldn't tell the difference that these were not unitarily similar matrices. And the reason for this is because this matrix B is not unitarily similar to some diagonal matrix. So I can't represent its unitarily similar equivalence class just by the diagonal entries of some diagonal matrix, by the eigenvalues. Not being unitarily similar to a diagonal matrix happens to be equivalent to the property that you don't commute with your conjugate transpose matrix, which is true for this matrix B. As you can see, if I multiply B by its conjugate transpose, I get this matrix with a 1 in the upper left. But if I multiply the conjugate transpose of B times B, I get this matrix with a 1 in the bottom right. So I need more properties than just the moments, as I was looking before. And generalizing this idea, I can take what are called star moments and see that the star moment AA star is equal to 0, but the corresponding star moment for the matrix B is equal to 1. So I can from this star moment, I can tell that A and B are not unitarily similar. Formalizing this to get a complete set of unitary invariants for non-Hermitian matrices, back in 1940, Specht proved that two matrices are unitarily similar if and only if all of their non-commuting star moments are equal to each other, their corresponding non-commuting star moments. Just to give an example as a definition of what a non-commuting star moment is, here's a non-commuting star moment in B and B star, where I take the star moment B, B star, B, B star, and I get 1. And just to show that the non-commuting aspect really matters here, the moment for B, B, B star is equal to 0. So if I take all of these non-commuting star moments, that gives me a complete set of unitary invariants according to Specht. So we can, just as we had with the moments, we can think about representing this as coefficients of some generating function. So I have my star moment generating function here, where S and T here are non-commuting variables. So just to show you, like the degree 2 term of this non-commuting generating, this star moment generating function gives me this, when I expand it out, gives me this term where I have a coefficient times some ST term and a coefficient times some TS term, because S and T don't commute. So these are really 2 different coefficients. So in the single variate case, we were studying the moment generating function, which was the coefficients of a single variate formal power series. And now we have coefficients of a non-commuting multivariate formal power series. So this is a much more complicated object. So we thought, okay, well, can we still get mileage out of just studying what I call the relaxed star moment generating function? So here I still have A and A star, but now instead of S and T, which don't commute, I put in the variables Y1 and Y2, which do commute. So the second order term for this generating function just gives me a single term Y1, Y2, where the coefficient is the sum of the coefficients from the ST and TS term, because now Y1 and Y2 are commuting. These really are different generating functions, and it starts to really make a difference once you get to 4th order terms. Y4 might make sense if you're familiar with free probability. All right, so just as before, we studied the moment generating function, but now I thought, okay, what if we take our relaxed, our term from our relaxed star moments, Y1A plus Y2A star, and plug it into our characteristic polynomial instead of plugging it into our moment generating function. So I call this, I choose to call this a non-Hermitian characteristic polynomial. It really does generalize the classic characteristic polynomial. You just have to plug 1 in for Y1, 0 in for Y2, and you get back the classic characteristic polynomial. And very important to us, this is also this function is unitarily invariant. So if I take any unitary transformation on my underlying matrix A, it doesn't change its non-Hermitian characteristic polynomial. And now looking at our example from the last slide, our matrices A and B, I see that the non-Hermitian characteristic polynomial of my matrix A is x squared, but the non-Hermitian characteristic polynomial of this matrix B is x squared minus y1, y2. So since this is a unitarily invariant function, I know that because their non-Hermitian characteristic polynomials are different, these are not unitarily similar matrices. Of course, if I plugged in 1 for y1 and 0 for y2 to get the classic characteristic polynomial, this term would drop out and I wouldn't be able to tell the difference anymore. A nice thing about this is that the coefficients of this non-Hermitian characteristic polynomial can be related to directly related to the relaxed coefficients of the coefficients of the relaxed star moment generating function through a generalization of Newton's identity. So we go back and forth between these frameworks. And so that's a nice property. But now, as you see, before we were studying single variate polynomials and their roots. Now we have multivariate polynomials. What can we even say about these objects? So one thing we can say is one way to look at this, which also gives us some nice pictures, which is a nice thing for a presentation, is looking at these things called higher rank numerical ranges. So here, this picture corresponds to one matrix, and this corresponds to a different matrix. The black points represent their eigenvalues. So both of these matrices have the same eigenvalues. But these lines are what represent what are called higher rank numerical ranges. And you see that these two matrices have different higher rank numerical ranges. Now, computing these higher rank numerical ranges is a direct function of the non-Hermitian characteristic polynomial. So knowing the non-Hermitian characteristic polynomial allows us to compute these objects, these higher rank numerical ranges. So this matrix that we're representing on the left is a matrix that is unitarily similar to a diagonal matrix, which means that its eigenvalues give you all the unitarily invariant information you want. And you can kind of tell that the higher rank numerical ranges are just functions of these eigenvalues. But on the right, this corresponds to a matrix that is not unitarily similar to a diagonal matrix. And therefore, the higher rank numerical ranges actually have more information beyond just what their eigenvalues represent. If you're familiar with the numerical range, this is just the generalization of that concept, because the outermost higher rank numerical range is equivalent to the numerical range. These really became popular starting around 2006 because they have a lot of other nice properties like interlacing properties and stuff that I won't get a chance to get into that helped them become useful for quantum error correcting codes. But yeah, so we have these nice pictures, and this is one way to see information beyond eigenvalues from these non-Hermitian characteristic polynomials. So I'm going to generalize these non-Hermitian characteristic polynomials one step further and define what I call a multivariate characteristic polynomial, where here, instead of just taking two matrices A and A star that are conjugate transposes of each other, I take a family of matrices, A1 through AL, which don't have to be conjugate transpose or related to each other in any real way, and then a collection of commuting variables, Y1 through YL. And then I take the sum of the Yj, Ajs here and plug it into my characteristic polynomial and define a multivariate characteristic polynomial. So clearly, like if I just let A1 be A and A2 be A star, then this is a generalization of the non-Hermitian characteristic polynomial. And importantly, again, this is also a unitarily invariant function. And what I mean by unitarily invariant in this case is I do the same unitary transformation to every matrix in my family. So I transform every matrix A1 through AL by the same unitary transformation. And once again, this can be related to the relaxed multivariate moments by a generalization of Newton's identities once again. So you can go back and forth between the moment and this characteristic polynomial way of looking at it. But just like with Hermitian finite free probability, we're not just interested in individual matrix family. We want to perform operations. We want to do sums and products of these. So I define the multivariate sum, where I take a unitary transformation of every matrix in the family of matrices B. You take that unitary transformation uniformly at random according to the Haar measure and add it to the family of matrices A pointwise, and I call that the multivariate unitarily invariant sum. And I could also define a unitarily invariant multivariate pointwise product, where I do that same uniformly distributed unitary transformation on the family of matrices B and take the pointwise product with the family of matrices A. So now, just as before, this gives me a random matrix family. That's a really complicated thing to study. And I make it tractable by taking the expected multivariate characteristic polynomial. And amazingly, both of these are also just multivariate polynomial convolutions of the two corresponding multivariate characteristic polynomials of the family of matrices A and B for both the multivariate sum and the pointwise product. There are corresponding convolutions for these in free probability. This corresponds to the multivariate additive convolution of free probability. And this corresponds to what's called the free boxed product. So I'll tend to call it the finite boxed product because of that connection. And like I was saying, amazingly, this too is now a multivariate polynomial convolution. And by that, I mean that given the multivariate coefficients of my two original multivariate characteristic polynomials, I can directly compute the coefficients of the output multivariate polynomial for both the finite free additive convolution in the multivariate case and the finite box convolution. To derive these multivariate convolutions, the finite free additive convolution can kind of directly come out of just with some trivial algebraic steps. You can reduce this multivariate additive convolution to the single variate additive convolution and just get this multivariate additive convolution directly from our previous polynomial convolution. But this finite box convolution really is a new convolution that needs to be derived independently. It can't be reduced to like the finite multiplicative convolution. And in fact, this can be kind of thought of as like an all-encompassing finite free convolution, because every convolution I've talked about today can be represented as a special case of this finite boxed convolution. So let's talk about some of the algebraic properties of these convolutions. So it's commutative with respect to these multivariate polynomials. It's linear with respect to these multivariate polynomials. This is mirroring what we had before. And now I define a generalization of basic polynomials that I call multivariate basic polynomials, where here I just have a constant vector A and write it as a multivariate homogeneous polynomial in this way, where A is just some constant vector and B is some other constant vector. When I take their multivariate finite free additive convolution, I get another multivariate basic polynomial where the constant vector is just the sum of the vectors from my original basic polynomials. And for the finite box convolution, I just take the pointwise product of the vectors from my original two multivariate basic polynomials. So just as before, using linearity and multivariate basic polynomials, I can derive the multivariate basic polynomial decomposition, this corresponding theorem, where if I represent some multivariate polynomials, P and Q, as a weighted sum of multivariate basic polynomials, then their multivariate finite free additive and boxed convolutions can be written in this new weighted sum of multivariate basic polynomials in this way. And once again, just as before, if we put the constraints that the CJs are strictly positive or positive and sum to 1, and the DKs are positive and sum to 1, then we can write this in the language of classical probability, where we now have a random vector S and a random vector T that are classically independent. And I can write the finite free multivariate additive convolution by just summing these independent random vectors, these classically independent random vectors, or taking the pointwise product of these classically independent random vectors for the finite box product. So now we're going to derive the finite free multivariate additive central limit theorem, where I again have capital N families of matrices now. I have constraints on the first two the moments up to the first two orders, and I scale each matrix in these families by 1 over square root of capital N. I take the finite free multivariate additive convolution, capital N times, let capital N go to infinity, and it converges to this multivariate polynomial that I write as an expected polynomial, where here I get that this is a random vector S distributed according to the multivariate Gaussian from classical probability, which of course is the additive central limit theorem of classical probability. So this gives a nice connection there. So that's for the multivariate case, but we were interested in this special non-Hermitian case as well. So let's see what happens there. So now I put in the non-Hermitian constraints I would want for a family of matrices, and scale them all by 1 over square root of n, and take the same central limit theorem, and I get that it converges to this multivariate polynomial, which again I write as an expected polynomial, where here I have a random variable S, which is distributed according to the complex normal distribution, and this is the conjugate transpose of that random variable S. So this relates, as you would hope, to complex classical probability, and this is a non-Hermitian characteristic polynomial, so we can even watch the evolution of its higher rank numerical ranges. So I have a family of matrices with these black dots representing the eigenvalues of those matrices, and these lines representing the higher rank numerical ranges. And as I do this convolution more and more times, you see that the higher rank numerical ranges converge to these concentric circles, and actually the eigenvalues all converge to the origin. And the fact that all the eigenvalues just converge to the origin follows from our single variate finite free convolution under these constraints that the first two moments of all of my matrices are 0. So all the eigenvalues go to 0, but just knowing that is not all the information there is to know. With these non-Hermitian characteristic polynomials, we also get this information that gives us these concentric circle higher rank numerical ranges. All right, so let's see how this polynomial, which I call a circular Hermite polynomial, relates to these other fields. So it relates to random matrix theory. In fact, the expected non-Hermitian characteristic polynomial of any non-Hermitian Wigner matrix is a circular Hermite polynomial, where a non-Hermitian Wigner matrix is just a Wigner matrix without the Hermitian constraint. It relates to free probability, where actually if you take the relaxed star moments that are implied by the circular Hermite polynomial and let the degree lowercase go to infinity, then those relaxed star moments converge to the relaxed star moments of the uniform distribution on the complex disk, which is actually the additive central limit theorem distribution in non-Hermitian free probabilities. So that's the comparison we would hope for again. And also in free probability, they have this other way of defining circular objects, where they say take a semicircle object and I times the semicircle object, take their free convolution, and you get a circular object. And analogous to that, if we take our equivalent to a semicircle object, which is a Hermitian matrix with eigenvalues on the roots of a Hermite polynomial, and take I times an identical matrix, or a similar matrix with those same properties, and take their finite free convolution with non-Hermitian characteristic polynomials, we get a circular Hermite polynomial. But if we just did that with the classic characteristic polynomial, all we would end up getting is this constant polynomial x to the n, which is just telling us that all the eigenvalues, as we had on this slide, are going to 0. But the circular Hermite polynomial tells you everything about those higher numerical ranges as well. All right. Now I'm going to talk about the multivariate finite free multiplicative central. So now I have a family of capital N, a collection of capital N families of matrices under some constraints again, and I now scale every matrix in these families by raising them to the power 1 over square root of n. taking their finite box product and taking the limit as this number of families goes to infinity, and it converges to this polynomial, which once again I write as an expected polynomial, where here I get the multivariate log normal distribution, which is the multivariate multiplicative central limit theorem of classical probability. So here, once again, the hard part is computing this scaled multivariate polynomial, which we used some multivariate combinatoric identities and the multivariate generalization of Newton's identities. One interesting thing is, as far as I'm aware, at least, in free probability, the boxed convolution central limit theorem is not currently known. And the reason for that is because the boxed convolution is defined by Spiker in terms of non-crossing partitions. And as far as I'm aware, a definition, an analytical definition in the Voiculescu sense isn't known for the boxed convolution. So computing a central limit theorem, again, as far as I know, isn't known in free probability, but we have it here in the finite case. So that's the end of the new results I'm going to talk about today, but I do want to talk about a few future directions and conjectures briefly before I stop. So you might have noticed, given the mirroring structure, that I talked about the multivariate finite free additive convolution central limit theorem and the non-Hermitian finite free additive central limit theorem. And I talked about the multivariate finite free multiplicative central limit theorem, but I didn't talk about the non-Hermitian multiplicative central limit theorem. And the reason for that is that if you take a pair of matrices, A and A star, and another pair B and B star, and you do their unitarily invariant sum on these matrix families, I get two new matrices, which are conjugate transpose, a pair of matrices that happens to be conjugate transposes of one another. And even when I do the final, I get another multivariate characteristic polynomial that is a non-Hermitian characteristic polynomial for some matrix C every time. But for the multiplicative case, if I do the pointwise product of these pairs of matrices, A and A star and B star, this unitarily invariant pointwise product, I get another pair of matrices that are not necessarily conjugate transposes of one another. And related to that, the finite box product of two non-Hermitian characteristic polynomials does not necessarily give me it gives me some multivariate polynomial, but it does not necessarily correspond to a non-Hermitian characteristic polynomial for some matrix C. Again, as far as I know, so we don't have a polynomial convolution that keeps this property. We haven't been able to find one. And as far as I know, in free probability, they also haven't found such a non-Hermitian multiplicative convolution. So there's clearly something hard going on there. But amazingly, in free probability, even though the convolution is not known, with a lot of work, with some amazing work, Driver, Hall, and Kemp in 2019 were still able to find the free non-Hermitian multiplicative central limit theorem. So I figured, okay, let's just see what happens if I take a guess with, even though it doesn't have this closed property and everything. So I put in the assumptions, the non-Hermitian assumptions I would put in, and then just do the finite box product on those non-Hermitian characteristic polynomials. And I get some limiting polynomial, it limits out to some polynomial that has this form where I have the complex log normal distribution from classical probability here and its complex conjugate, which is kind of the form I would want, except this expected polynomial is not necessarily, or tends not to be, a non-Hermitian characteristic polynomial. Well, one observation I made is that if I just put in a minus sign here in front of, for some reason, then this expected polynomial does tend to be a non-Hermitian characteristic polynomial. So I can plot its higher rank numerical ranges, and I get, for some, this is for some value of sigma squared, I got these higher rank numerical ranges, which look very, to me at least, look related to the non-Hermitian free multiplicative central limit theorem that Driver, Hall, and Kemp found, and which they called the Lima being law because of how it looks. And I think these two things look similar. So that might be interesting to look into. A few more future directions I think would be interesting to investigate. So we have the non-commutative star moment generating function or multivariate moment generating function, but we only have the relaxed version for the characteristic polynomial. Could we define some sense of like a non-commuting characteristic polynomial? Does such a thing already exist, or could we define one? And that would give us then some sense of non-commuting elementary symmetric polynomials, and maybe even a way of going back and forth with some non-commuting generalization of Newton's identities. Also, in classical probability, you know, once you get multivariate probability distributions, you can start to define conditional probability distributions. So now that we have multivariate finite free polynomials, could we define some sense of like conditional finite free probability? Also, you see that the way we make this problem tractable is we have our random characteristic polynomial and we just take the expectation of every coefficient. So it might be interesting to also do what people call second order finite free probability, where you find the covariance of those coefficients or higher order. And this would be interesting because most of the applications, or all of the applications of finite free probability right now really are existence proofs. That was the case in the solution to the Catterson-Singer problem, or the existence of Ramanujan graphs. They show that given some collection of random matrices, some random matrix, there exists an instance that can bound the largest root or something like that. But maybe studying the second order stuff could give you concentration bounds like Chebyshev or Chernoff type bounds in finite free probability. Also talking about these Ramanujan graphs, currently they can only bound the largest root, and they have trouble simultaneously bounding the smallest root. But using these higher ranked numerical ranges that go around the whole complex plane, it's known that all the eigenvalues always are bounded inside of the largest higher ranked numerical range. So maybe that could help give you two-sided bounds, especially because they have these interlacing properties and stuff. And finally, this relationship to Ising models that we found with the multiplicative central limit theorem was kind of surprising. And maybe the algebraic structure of finite free probability could imply some sense of an algebra of Ising models. I'm not sure exactly what that means, but it was surprising. I think it could maybe be an interesting thing to do. All right, I really just can't express how grateful I am for everyone showing up. I really thank you for being here. Thank you for being part of my life. Thank you to the committee. I am so thrilled I got to present this whole, all this work to you. It really means a lot to me. Thank you to my family and my partner, Katie, for just your love and support every single day. Thank you very much to Audrey and to Tina and to Christina. I'm so lucky that you were at PACM while I am. You made this really much more caring and smooth of an experience than it would have been without you. And finally, a million times over, I really want to thank Adam Marcus, who's just the most generous friend, mentor. I cannot overstate how lucky I am to have had him as an advisor. Yeah, thank you again. Look forward to any questions, comments, anything anyone wants to say.
Questions?
I have one question. So one of the basic facts in sort of the Hermitian finite convolution theory is that if you take two real-rooted polynomials, then the convolution, the finite free convolution of them is also real-rooted. And there's also some inequalities relating the location of the roots of the convolution with the roots of your original polynomial. For your multidimensional convolutions, are there similar sort of facts relating the zeros of the polynomials with the convolutions?
So the zeros of the polynomials, so if you really just care about the so they're multivariate polynomials. So if you just care about the zeros, all I really can interpret that by meaning exactly is the eigenvalues, which is basically just reducing it to the classical characteristic polynomial. But I think more maybe at getting what you're talking about is this property here, where if you take non-Hermitian characteristic polynomials, so these are specific multivariate homogeneous polynomials, using those same theorems that you're saying, leveraging those same theorems about real rooting staying real rooted, you can prove that the non-Hermitian convolution of these two non-Hermitian characteristic polynomials gives you a polynomial that is the non-Hermitian characteristic polynomial of some matrix. So that is a theorem, because that's not every multivariate homogeneous polynomial is. I don't know if that answers your question.
Well, it does partially. I was wondering also if you could, do the eigenvalues of the C matrix, are they constrained somehow by the eigenvalues of A and B?
Yes, again, using the exact same thing again. So here,
okay.
there is an interlacing property once again.
Okay.
And it's because the way that you get those higher ranked numerical ranges is by essentially plugging in for this y1 and y2, like e to the I theta and e to the I minus theta, e to the minus I theta, and then so just projecting it to being a real rooted polynomial in each direction, in each radial direction, and then taking a convex hull of.
Okay.
But those same interlacing properties come up. It is also a little bit complicated in some sense of getting the bounds, but it's doable because to get the bounds in the applications that have been used before, you needed to be adding rank 1 matrices. Oftentimes, when here you can't do that, but there are related bounds for like rank 2 matrices that you might need to add that still give you these interlacing properties. And so you can get some sense of like a non-Hermitian Caddison Singer or something like that using these interlacing properties as well.
Okay. Okay, that reminds me of, go ahead.
I wonder, I mean, in some of the results, you could choose several expressions to begin with. So, like, for example, in this basic polynomial decomposition, you could start with many expressions, right, which the expression was not unique, and still the result always holds. And I wonder if you start with different expressions, so it seems you get some identities, right? And I wonder if those are interesting or they are obvious. So if you take you start with two different expressions, and then you know that a result should be the same.
So there are interesting things that come from this by picking different expressions. So one thing that's really interesting, I think, which helps you extend from just looking at it in the classical probability sense, but looking at it in this basic polynomial sense, is that I can make these weights negative as opposed to just always positive and summing to 1. And in doing that, I can change the coefficient of the x to the n term no longer needs to be 1. So I could actually make it so that I can do a degree n basic polynomial decomposition for a polynomial of degree n minus 1 or n minus 2 if you wanted. And actually in finite free probability, there are these things which relate to matrices through random projections where you might want to take finite convolutions of like a degree n finite free convolution of polynomials of degree less than n, and that can be done exactly with this basic polynomial decomposition. So I just give a basic polynomial decomposition where the sum of these decays all sum to 0, and then it knocks off that x to the n term. So there are interesting implications that come from different ways of writing it in this basic polynomial decomposition, and also ones that you don't necessarily get when you only think about it in this connection to classical probability, where they're constrained to be positive and sum to 1.
Okay.
Okay. Let me ask my second question then. So I remember in one of the first papers on finite free convolution, maybe it was by Nikhil and Adam and Dan, that you can interpret derivatives of polynomials as in terms of expected characteristic polynomials of minors. And I think, in fact, there's a key lemma in some of those basic properties of free convolution. Do you know of any sort of multi-dimensional version of that statement?
Yeah, so everything in my actual dissertation, every result I gave here, which I related to classical probability, I also gave again in the language of differential operators, which, like, so this theorem actually was previously known, proven by Adam with respect to differential operators. I also, in my dissertation, which I didn't get to talk about here, was able to represent, give, like, I don't know if you know, like in those finite free papers, they have this thing where they define like p hat, which is like the the polynomial on differential operators, and they allow them to turn the finite free additive convolution into just multiplying these p.
Right, I remember, yes.
You can do the same thing with a different differential operator for the multiplicative case, where you have x dx, and the new polynomial, the transformation is basically equivalent to the transformation from using the basis 1x squared all the way up to xn to doing the Newton basis, which is like the partial factorials. So you can go back and forth using like a Vanderbilt matrix between those coefficients and this like multiplicative p hat, like all like p tilde or something. And in the multi-dimensional case, in terms of the minors, that's how this new convolution has to be derived once again. And there's also language with these differential operators where all of these results, which I chose for the talk to present as connections to classical multivariate and complex probability, could be written as these like multivariate differential operators, partial differential operators, and that is in my in the paper. It just wasn't in the talk.
Okay, thank you.
So maybe I'll ask a question about so in the finite limit, also the non-Hermitian one, it basically implies that the roots of the that's the roots of these polynomials converge weakly to the roots of converge weakly to semicircle or circular, right?
Mm-hmm.
Or no, sorry, not circular. Converge weakly to the Hermite polynomial roots or to the circular, the circular Hermite polynomial as you define them. Could you say something about the rate of convergence, and could you say something about the support? So could you say something about the extreme roots?
So again, roots is a weird way to talk here. So I wish I could say something about roots, but I think, I don't know, there might be an approach using second order finite free probability, which gives you some sense of roots here, but really, because
no, maybe you misunderstood. I'm just saying that you have a sequence of polynomials of degree little n, right?
Yes.
And their roots are approaching the roots of a Hermite polynomial.
In the
in just the Hermitian case. So I was just asking, can you quantify the rate? So you can probably get some bound, because in your proof, if you go through the classical CLT, you get some bound for the rate of convergence of that, and maybe you can translate that.
So it is convergence in moments, but it's convergence in moments in this weird way where I have these, because I'm not actually computing all of the moments. I'm computing this like these relaxed star moments where as I have here, for these terms, I sum together all of the ways in which they differ. So there actually might not be a non-commuting, a commuting distribution in the classical sense for a commuting variable that has these relaxed star moments in the finite case. And yet in the limit, as it goes to infinity, those relaxed star moments converge to the relaxed star moments of the uniform distribution on the disk. And why that works, why these relaxed star moments are enough in that case, is intimately related to the fact of, in free probability, these are diagonal elements. So basically the circular law has this nice property where it's an R diagonal element, where this fact that S and T, all the terms for ST are the same for TS. It doesn't, it treats them as commuting, and that's why our relaxed moments match up. But it might not even be the case that there is a distribution for some finite n that corresponds to having these relaxed star moments. But that's why the way that we talk about it in the finite world is with these like higher ranked numerical ranges, or with the polynomial itself. And then the convergence is, so it's kind of like, I'm not the one, I don't know if I should say that I support or don't support this view. I'm not the one to make up this visualization here, but it's kind of like you're converging like this instead of converging like this, is how people like to describe it in the physics world. Like you don't really exist until you hit the limit, and then you match up. So the type of convergence is a weak convergence in star moments in a sense, but the distribution might not even exist except in the limit.
Mm-hmm. I mean, I guess in the Hermitian case, the distributions do exist, but so the question does make sense in that case.
Yeah, well, I mean,
that's a different question. Huh?
For any, I think, right, for any collection of, yeah, so that you have these finite moments and they do correspond to some underlying distribution, this collection of moments, but if you give me any collection of n moments, you're going to have some distribution that it corresponds to. But if you give me any collection of these like star moments, you might not, and you don't.
Okay, thanks.
Okay. Adam, should I take you all to the breakout room now?
Yeah, if there are no more questions.
Okay.
Sounds good.